Thanks, David, for a great talk. It's my pleasure to introduce our second speaker, Abhinav Gupta, who's a faculty member at the Robotics Institute at Carnegie Mellon. Abhinav's done a lot of cool stuff on self-supervised learning, and he wants to build interactive systems that can learn on the go. He's won way too many awards for me to kind of list, so I'm really excited to hear what he's going to speak about today. The floor is yours.
Thank you. Right. So it's nice to have David give this talk because some of the work actually builds on this stuff. But for my talk, I'm going to be focusing more on robotics and trying to do like generative, like how do you bring large scale learning to robotics? It's an actually very different question altogether. So like all other fields, like vision, NLP, robotics has also seen a dramatic improvements over the last few years, especially in this area of data-driven self-supervised learning for manipulation. Starting from the work that we did in 2016, where we for the first time scaled up dataset collection to like 700 robot hours, 50,000 examples, to now a lot of papers you might have seen from Google, like RT1, RT2s, and so on and so forth, which are now using millions of examples and years of data from human operators and so on. But unlike other fields, right, what is the biggest issue in robotics is still the data, right? So if you think of learning a foundational model or generative model in language, it's easy. The data is out there on the web, right? Wikipedia by itself is so much data on the web. If you think of vision, what David was talking about, these stability AI models and so on, they're learned on billions of images because these billions and trillions of images exist on Instagram, Facebook, whatever. I mean, there are so many websites where photo sharing is happening and data exists. But now when it comes to robotics, this is not a luxury that robotics people have. There's no data out there of robots interacting with the world that you can collect and use it to train these large-scale models themselves. And so, unlike other areas, the biggest issue in robotics still remains the data. Once we can get some data, once we have some grasp on the data, we can then think of answering these questions, what these models are learning and so on. But in the field of robotics, there's still a struggle with the data. The biggest data that you have seen is this Google RT1 paper, which basically had human operators collecting data over 2 years. Like they had teleop data being collected, and that also in like 4 Google kitchens that there existed out there. So this data remains the biggest issue. So how do we go about this data scaling problem, essentially? The first way is for the rich people or the rich institutes or whatever you want to call it. This is scale the physical infrastructure. And so the idea is just buy hundreds of robots. Like nowadays, companies have thousands of GPUs. Maybe you can buy hundreds of robots and have them collect data in parallel. And hopefully that will help solve your problem. And so this is the answer, for example, Google used around 2019, where they started collecting large-scale data for manipulation. And they ended up collecting 1 million examples. It's still 1 million over like 5-6 months with all these 14 arms and so on. So clearly, I mean, this physical part is very hard to scale as well. The second and the most common answer that you will hear in robotics is you using something like sim to real. The idea is you train your exam data like policies in simulation and then transfer them to the real world. But simulation has all these different issues. For example, there is a visual domain gap. Like these things do not even look very realistic. There could be physical gap, right? I mean that the kind of physics that exists in the simulation might not exist in the real world. But the biggest issue with sim to real argument is the diversity. Like it takes lots of engineers to just simulate one scene perfectly. Now think of if you have to simulate thousands of scenes, is it really scalable to build these simulators at that level itself? There's a philosophical argument as well that someone could argue that that's building a simulator is a much harder problem than solving the robotics problem itself, right? Doing actions, I mean, do you simulate each and every pixel in your mind before you do actions? Or do you just do actions directly from the current environment itself? The third option is, maybe we just don't need data. Maybe there are simple ways of getting this data around the data problem. That is imitation learning. Have humans do these tasks, or now it becomes more like a supervised learning than the generative learning as well. So in this case, humans are guiding the robots to collect some positive examples, and these positive examples can then be used to train policies themselves. But even these kind of imitation learning data collection is very difficult, slow, and mostly has been attempted in lab settings. And even here, it has been found out that you still need lots of scaling. Still needs millions and tens of millions of examples before things started working reasonably well. So the core issue for robotics is collecting any kind of interaction data is very, very hard, because the world changes with the one action that you do. It's not a static data problem like in vision or NLP. As the world changes, the new data comes. So you have to basically, this whole interaction data is very, very hard to collect. And so one idea is that can we reduce some of these active data requirements, these interaction data requirements? And so always, even my question kind of hinted that whenever I am in a problem, whenever I don't know the solution to how something should be solved, I always look to humans. Like, did human collect that much interactive data to learn how to do actions? Or is there something else going on in the case of humans as well? And so, in fact, I was a computer vision researcher when I did my PhD. And my whole transformation to robotics actually was driven by this as well, that when I look at the babies learning, it seems that they are doing a lot of physical interaction. They touch things, they put things in the mouth, they throw things around, and so on. And this is a video which I have been showing for last 4 or 5 years to argue that vision people should be doing robotics to learn vision features, good vision features, and so on. But this is kind of an incomplete story, right? Because all these children are interacting with the world, but the amount of interaction data is still significantly dwarfed by the amount of passive data that they are using. And by passive data, I mean just observing everything around them. Here, their actions are not making any difference into the world. They're observing whatever is happening around them. They use that data, like they observe their parents opening a microwave, their parents pour tea from the kettle, and so on. That data, in combination with what they are doing in the world, that active data, is what makes their policies and their approaches. And so, in my case, if we can use this as a inspiration, that babies are using lots and lots of passive data in conjunction with the active data to actually scale up their learning. Can we do something like that in robotics as well? Because if we can use passive data, then we can all harness all the passive data from vision and so on to actually scale up our generative learning or whatever learning that we want to do as well. And so that is what I want to explore in this talk. That can we bring for the first time large-scale learning at the level that all other fields are in NL AI are doing, like billion images or billion scale and so on, into robotics. And the way we are going to do that is for the first time use passive data. And by passive data, I mean observing other humans or other agents in the world doing actions and interactions with the rest of the world to use them to learn about the models and then transfer them to robotics somehow. And so that's what we are going to explore. And I've been exploring in recent years as well. Now, throughout the talk, I'm going to build how can we actually use these kind of approaches, like how can we use passive data to do it? The first approach is very simple. This is kind of, let's use all the vision data to do some pre-training and then fine-tune with these pre-trained models themselves. So let us look at what a robotics algorithm looks like, right? In a robotics case, you have a visual input, that is a camera looking at the object that you want to interact with. And given that visual input, there is a neural network or whatever the model is that needs to give out the actions that the robot should do to perform an action, right? And so in this case, the mapping from visual input to actions requires you to first understand the visual inputs, right? You have to have an embedding of the vision data, and then you have to convert that embedding, like the understanding of the vision, like there is a pointer here and there is a laptop here and so on. That has to be converted into actions. So there are two parts of it that has to be learned. And that's what makes it really, really hard. Like you still need, like if you think of just doing something like object detection, that requires billions of examples. Now you're saying now I don't only have to do object detection, but I have to do actions on them. So now it has to be very fine-grained. So think of how much data it would require to train a vision algorithm to get that kind of an output. And so one possibility is to not do this like end-to-end system. Maybe we can do something modular where the vision system, they're going to be two networks. The first one is going to take visual input, get some kind of learned visual representation, and then the learned visual representation will be mapped to an action. And if we can do this kind of modularity, then we can pre-train the first part, like the visual input, like the visual representation, which is going to work for robotics themselves. And this is the first approach that how we can use large-scale passive data for robotics itself. And pre-training is, of course, very, very common. We know all the places where pre-training has worked, like all these large language models, you first pre-train on large amount of text data, and then you fine-tune it for your own applications. Similarly, in vision, pre-training is like a given. Everything is pre-trained either on ImageNet or these large models like CLIP is trained on 400 million data set, and then fine-tuned for your tasks themselves. And so we started exploring, can this kind of a philosophy work in the case of robotics? Because until 2022, most of the pre-trained models would not work in robotics at all. And so in 2022, we had a paper in ICML, and that's why we call it the unsurprising effectiveness of pre-trained models, because everyone thought the pre-trained models in vision do not work in robotics. Even though if you think like intuitively they should work, why would these models not work? And when for the first time, we actually tried to do these a much more extensive study of using an ImageNet pre-trained model for a task like habitat, adroit, like all these manipulation tasks and navigation tasks. And for the first time, we could show that actually ImageNet models would work. It's just that everyone is using FC7 last layer features, which are very highly semantic. You don't have to use the last layer features. You have to use before the last layer features, and then things will start to work in robotics as well. And so it was a huge eye-opening thing for the field in the robotics that, in fact, pre-training could work. And in this last 2 years, there has been an explosion in robotics on trying to actually pre-train the features to use it for robotics tasks. We had our own paper in 2023 where we actually used egocentric data like this to pre-train visual representations. And the way we are training these representations is by trying to make sure that as the state of the object changes, the feature representation changes. There's a language term which makes sure that if you're learning about laptops, you should only be using laptop images, and sparsity, that the representation should be sparse. And we showed that if you actually learn a good representation from this Ego 4D data, it can transfer to new task and new environment significantly. And you can do like with 100 examples, you can train a good action models themselves as well. But then I wanted to go back and see, are these actually models learning? Like, it's always good to understand that if something is working, is it working because the reason that you think you're working, or is it something else? So this year in Coral, we actually started exploring, is it the data set? The idea was that we are using this kind of manipulation data set, like egocentric data. So what we were thinking was that because we are using the data of human-object interaction, it is able to get these intricacies of human-object, like in object interaction, the physics of objects. And that is what this model is able to learn. And that is why we are getting some of these good results and so on. So we wanted to explore that whatever we are learning, that these pre-trained representations, are they learning these intricacies of human-object interaction or object physics, or is there something else which is completely happening here as well? So what we did was we took this simple mask encoder. This is a representation learning approach, which is very similar to the way LLMs are trained, where you hide some of the text from the paragraphs, and then you try to predict those hidden text. The same way in the image, you hide some of the content of the image, and you try to predict the rest of the content. And that's how you train your representation as well. So we use this mask encoder as a way to pre-train our vision models. And then we tested it on 5 different data sets. ImageNet, which has nothing to do with human-object interactions. 100 Days of Hands is a wild human-object interaction data set. Ego 4D is a very controlled way of collecting data set for human-object interactions. Kinetics does not have much of human-object interaction. It has actions like running, jumping, and so on. And RoboNet is exactly robotic-style data set. And we wanted to see how would the simple mask encoder perform on all these 5 different data sets. And hopefully, our hypothesis was that egocentric or 100 Days of Hands would work the best. That would mean that these models are able to extract something out of the manipulation domain itself. So something out of the manipulation domain itself, which is kind of what we wanted essentially. And so we are going to test it on all these tasks like behavior cloning, like in simulation as well as in real world tasks like pouring, block stacking, toasting, and so on and so forth. And so here is some of the very surprising results that we got for the first time, that interestingly, the more aligned the data set was to the task of like the more object interactions it had, the worse it performed when it comes to pre-training. So this is like completely opposite to what we thought. We thought that we are pre-training it in the manipulation domain so that it can learn something about the human object manipulations, and it can learn about manipulation. But it turns out ImageNet, which has nothing to do with human object manipulation, is actually giving the best performance when it comes to pre-training representations. And in fact, ImageNet is again able to beat most of the other SOTA baselines that have been coming in the last 2 years in hundreds of papers and so on. So one hypothesis was that ImageNet is much more diverse. These data sets are collected in one kitchen, few kitchens, and maybe diversity is the one which is missing. So if we can add diversity with the domain, maybe that will solve our problem. So we've created these soup data sets, which is using data from all the different data sets into one common things. And the idea is that as you increase the size of data in the soup, the performance should improve because it has more and more manipulation data in the soup as well. But even that did not work. And so the summary in our mind was that these approaches, mask autoencoder or contrastive learning approaches, the approaches that learn pre-trained representations, are not able to actually use the manipulation, the object interaction itself to solve these tasks. So the question is, how do we actually use this idea that the object is like laptop can close like this, and how do we use this manipulation information from all these passive data to actually use in robotics? And so the approach that we went for is to try to explicitly learn it. Rather than having these kind of models that actually predict the pixels, let's try to predict the affordances themselves, and maybe then we can actually try to make these work themselves. And so the goal here would be is that take all these amazing, like large-scale data sets of human-object interactions and try to learn affordances. That is, given an object, what actions or like how can a human hand interact with it, with that object itself. Now, and because if you can learn these affordance models, then we had approaches which can actually train the robotics on top of these results for different policy learning and so on. And so the biggest problem in learning affordance models is that this whole multimodality problem, right? And so if you think of a bowl, there are so many ways you can interact with a bowl. If you're going from the right, you can do the right, pick it up from the right, or you can pick it up from the left and so on. And because of multimodality, if you do very large scale learning, it kind of mushes it up and learns the mean, which is not even the answer in many cases. And so to get around this multimodality, so that is why this has been really hard for any of the supervised learning approaches to do this stuff. And that is where the whole generative models, the diffusion models that David is talking about. We wanted to explore that, like David wanted to explore, is there geometry in it? We wanted to explore that these pre-trained generative models, will they have hidden human-object interactions and the physics of human-object interactions inside them as well? Because if they have, these generative models predict the whole distribution. So the multimodality problem is gotten rid of. We don't have to worry about the multimodality problem. They will be able to generate these different outputs by sampling different noise vectors. And then we can use any of the noise vectors that we wanted to build on top of it. So this is a work with my student Judy, and Shalini also is here, who is a co-author in this paper. And so the idea was, we wanted to solve this affordance problem. The way we are going to do it is we are going to build on this huge work in the diffusion models. So we'll given an image, we'll generate an image of an object with the hand. And now from that, once you have predicted a hand, we can just start to now do the human, like mocap or Frankenstein mocap or any human hand pose estimation to figure out how should you interact with that object themselves. And our hope is that this diffusion models, which are learned from billions of images, have somehow learned about human object interactions themselves, essentially. But there is one problem, and I think this is something which you might have seen a lot. So I started going into the web and see, okay, how does a human object interaction work? It turns out these diffusion models are really good at predicting scenes and stuff and so on, but they are really bad at predicting hands. And so if you go and start like diffusion, like generated images for hands, you will see all these kind of weird images on the web when it comes to hands. And these are just hands interacting with hands. If you go for hand interacting with objects, things start to become even worse. And so this kind of falls in the realm of the spoke and bike and the cat having two-tail example for diffusion models, essentially. And so the idea was, how can we solve it essentially right now? So we came up with this idea that maybe the problem is too hard. We need to guide it with some structural priors of the world, and that will make it a little solve problem. If we learn that user diffusion models from like in a pixel way, there are not enough constraints to learn these properly. But if we actually take these pre-trained diffusion models, but then fine-tune them with a lot of structure, that would actually help us solve this generation problem, and it will be much more realistic generations that you will get out of it. And so our idea was to bring in this structure with a two-step process. The first is, you only predict one hand, for example. The idea is that given an object, predict a one hand, and it will be a very parameterized prediction, essentially. And then when you predicted the hand, you go and predict the content of it. So at least we'll not have 2 hands and 3 hands and so on and so forth. We have basically structurized this whole image generation, at least for this purposes, so that we don't have this problem of like generating weird hands and so on. And so the idea is actually very simple. The first part of the process, given an image, generates the layout. The layout is defined by the X and Y location of the contact, the palm, the width of the palm, and the direction at which the hand is approaching the object. And the idea is very simple. You basically take a noise image and you condition it on the original image, and you try to predict the hand orientation. I'll just do it again. And these are showing the how temporally hand locations are predicted for the kettle example as well. Now, once you have predicted the hand location, now you tell your diffusion model to say, okay, now can you put a hand in there? And that will be much easier problem. And hopefully now it knows it has to produce one hand only, and that's it. And so this is how you basically give a noisy image and this as like a condition, and that produces a human or like an interaction with the kettle itself. And so this is the final example that you get. And so you can see by imposing some structure, like our own knowledge, we are able to now for the first time make human object interactions work, which was not at all working in these diffusion models. And there are lots of examples, by the way, on Facebook also with different researchers showing how diffusion models fail on human object interactions as well. And so this is just saying that we actually fine-tuned the pre-trained model. Now, the biggest issue here is that once you have extracted the image, this image of human hand interacting with the object, then you can use any off-the-shelf human hand pose estimator to actually figure out the 3D pose of the hand, which can then be transferred for the robotics task, as I was showing in the simulations themselves. The good thing about this is because it's a generative model, you can actually do stochastic sampling, right? Different noise vectors will generate different hand positions and different layouts. And so basically, we are showing that for a single kettle, you can actually have these different hand ways you can grasp it. And this is good, right? Because otherwise, if I was doing it in a supervised, any large-scale manner, most of these will be merged into one final answer, and it will be a very blurry image that you will get. But here, because it's doing the whole distribution prediction, you can get actually very good hand location as well. Now, to make this work, of course, you need the original image without the hand, and then you have to produce the hand image. So it is conditioned on the without the hand image. But so you need a data set which has objects without hand and objects with the same image with hand. And so how would you do that? So to do that, we just basically took the human and object interaction image. We did the hand mask detection, removed the hand, and then did in-painting with the state-of-the-art in-painting model. Of course, this in-painting model would change the object a little bit. So we made sure that we trained it with both the objects, like did all these augmentation techniques and so on. But we could generate the data set where there'll be an object without the hand and then the corresponding object with the hand. And this could be used to train the content net that I was talking about, that given our layout, how would you generate it? And so we tried it like this is the way we created the data set just to show examples. These are all on the left are all the ground truth images. On the middle are like all the masks like detected of hand and the layouts that should be predicted by these models. And then the hand removed in the third column. And you can see in painting and all this stuff does a pretty good job. So we really have a really good data set of objects without hands and with hands. And that could be used to train these diffusion models for predicting human hands in the scenarios. And so here are some of the more interesting results. So here is a held out results on HY4D. Like these objects were not seen before, and how you can see all the different interactions that the hand can do with the bottle. Here is an example on an Epic Kitchen dataset. Again, trying to show different ways of grasping the same object and grasping the same bowl. You can compare it with other approaches like GAN hand, which has neither image synthesis nor iterative approach for improvement. Post diffusion, which does not have image synthesis but an iterative method of improvements, and our approach, which has both these things. And you can see our approach seems to generate much more plausible human object interactions. This is an example on out of domain, like in the wild data set, like there could be multiple objects and you still predict how would you do this. And again, the idea is to show that these diffusion models have a lot of information about the human object interactions. Of course, you have to work hard to extract them out of these diffusion models. We also tried to compare, like if you did end-to-end versus end-to-end will have not only have problems with hand, but even sometimes like prediction of location of hands, of how it should interact with and so on. And so we actually compared if you did end-to-end diffusion without the layout and content net, you will not get good recalls over the contact, like different data points it can contact with and so on. Another reason we actually went with the two-step is, and David was talking about it, that diffusion models are starting to have control. This is exactly what we found, that with these two-step architectures, we can actually control a lot. Like you can actually change the layout based on a human input. Like human will say, I want to have a human hand estimation from this angle. And now with changing layouts, you will have a changing ways of grasping. So you can actually control based on the layout net how the hand should grasp and so on. You can also combine it with another state-of-the-art approaches. Like there are approaches which predict the heat maps of how human hand should interact with the object. And so here's a heat map that in the case of bowl, you can pick it up with 2 locations, and then you can basically control the layout net to sample in both these locations and predict how the hand should grasp it as well. And there's another example that you can do it over multiple scenes and so forth. Okay, so this was the second part and second approach. Let me just see. Okay, where we actually use the images themselves to learn about the static affordances. And for the first time, we are actually able to extract manipulation, like human object information out of these manipulation data sets, which was very hard to do previously by even stability diffusion, like diffusion models themselves, or even like all the contrastive learning or mask autoencoder kind of approaches that we have been seeing. But this approach still only is focusing on statics, right? It's saying that given an object, how should you go and interact with it in a static manner? But we want to learn much more, right? We want to learn that you can press this button, you can close this laptop. I'm not going to close it, and so on. So you want to learn all these dynamics from the data out on the web, rather than just saying that I can hold it here. You want to know that I can hold it here and then start to close it and so on. So the question is, how can you go even a step further and not just worry about the static extraction of human object, but more like dynamic extraction? Like how can you manipulate these objects themselves? And so this is a work with Homanga and Shubham and Vikash. And before I go into how the approach works, I think we want to highlight, because this is probably the best manipulation result out there in terms of the diversity of the kind of things it can do. So this is purely learned from large-scale videos of human, like Ego 4D and Epic Kitchen combined together. We are basically learning how to interact with the objects in the wild. And you can see that it can open doors of microwaves. It can open drawers. It can put lids on the things. And even in the wild, we have tried it, like on a kitchen it has never seen before. The robot hand does very reasonable interactions, essentially. And so the idea is we want to learn all these diverse interactions without collecting the large-scale data that you have, like Google had to collect with these teleoperators, essentially. So how do we do that? We are going to use the large-scale passive data of Ego 4D and Epic Kitchens combined together. So this is more than tens of millions of frames. And we are going to learn how human hands and the object you are interacting with changes over time. And so the red shows the object that you're interacting with, the green shows the hand, and we are going to predict the mask. Instead of doing it in the pixel space, we are going to predict in the mask segmentation space. And again, these generative models are really good at predicting these segmentations themselves. Again, something that David was also showing, that these models can do really good on that axis. And so given the initial image and the goal image, we first predict the human plan of how a human would do it. And we'll predict the mask and the human hand with the plan. And then we will have a translation model that will convert a human plan into a robot plan. And for training this model, which converts human plan to robot plan, we use small number of human and robot data aligned together. But it's very small number. It's not a huge number of examples that you need to train this model on. And so the approach is very simple. Given a goal condition and the initial image, you take the noisy images, throw in the noisy images, which will predict the human plan of how human should, like if you have to wipe this countertop, how the wiping should happen. So your hand should go towards a cloth, then it should basically move around the cloth and so on. Once you have the human plan extracted in terms of mask, you give this human plan and the goal image and the current image to a transformer that will actually predict the action the robot should take to achieve this human plan in the real world. And this is so as simple as that, this approach. And hopefully The idea is that with the very less example, the second model is trained on very less robot examples, but it can actually use all the data that like tens of millions of videos of egocentric data to actually do tasks that it has never seen before, for example. And so we are going to test it on 3 conditions. Mild generalization is the same object that you have seen in training data, but now tested in a very different configuration. Standard generalization is a completely different object instance, but the same category, or a combination of the object and multiple objects and scales that you have never seen before. And strong generalization is completely unseen objects, completely unseen scales, and we see if they can actually transfer nicely. And we are going to do it in 2 settings, a tabletop setting and the real world setting, where the robot will go to the real world kitchen and try to do these interactions themselves. And so here are some of the examples, like my opening up of a microwave. On the top is the goal image. Then you have the human predicted plan of how would you open this microwave. Like you would do something like this and the mask will change something like this. And then on the bottom is how the robot actually performed these actions, like opening of a drawer or switching on a micro toaster and so on and so forth. Here are some more examples. These are again in the wild examples they've never seen before, because this kitchen was not in the training data, but we tested it in the training. Like we took the robot to the kitchen and tried to test it out there. Another example of strong generalization, these kind of objects were never seen before. And some of the even tasks like scooping cereal from a bowl was not seen at the training time at all, but it was there in the egocentric data. And that's the key to highlight here. We are able to extract information out of this human object egocentric data and the transfer to robotics for the first time, essentially at this scale. Much more examples of opening of a jar, closing a lid, closing microwaves, and so on. Here are more examples. I think, with the amount of robot data that we have used, this is like amazing that how it can do so many things. Because none of these examples have ever been seen before by a robotics perspective. It's purely from egocentric data. It's able to extract all this information. Okay, to summarize, I believe that passive data is the key to large-scale learning in robotics, right? We'll probably never have millions and trillions of examples like we have in vision and NLP for training large-scale models in robotics. And so what we have to do is we have to hop onto this passive data, these videos of human interacting with objects and other agents interacting with objects to build our portfolio of large-scale learning in robotics. And today I talked about 3 ways how we can use this large-scale passive data to use in robotics. We can do pre-training of representations that seems to work, but doesn't seem to really exploit the manipulation, the physics of objects and so on, the geometry and physics of objects. Then I talked about the affordances, which kind of focuses on geometry of objects a lot, like static geometry, and tells you how can you extract affordances of objects and so on. And finally, I talked about how you can actually use the object physics themselves, like opening of drawers uses the physics of sliding and so on. And you can actually achieve these tasks and transfer it from egocentric data to robotics for the first time. All right, that's it.
Thanks. I can't resist asking what is essentially the cat straight back at you, right? Which is, if you think about a process for generating grasps the way you've described, it is going to be, the game here is always in the tails. The reason you benefit from immense quantities of data is you will see relatively common grasps. The reason that Stable Diffusion is so bad at hands is it doesn't see them do all the things they can do, and as a result, it's a bit confused about where all the bits and pieces are. When is stuff so deep in the tails that to be able to synthesize grasps, you need some kind of structural model of a hand as opposed to an observational model?
Right.
That's just your question about the cat in different language, but yeah.
Yeah. So most of the cases we are moving from more like a pixel kind of model of hand to more parametric model, like more man, I think something like that. Like it has a 60-dimensional model of hand and so on. But I think for me, I think the issue is completely altogether. If I was in vision, I would ask that this is my problem. In robotics, this is not my problem. Then I cannot do even a head, like the main part of the grasp. Robotics is, so for me, if I can actually solve 80% of the grasp today, that's a big victory for me. and then I will go towards a tail, essentially. So I think if you think of AI, I think all the fields behave differently, and robotics has, I would say, gone at the most back of the AI field just because of the data issue. All other fields are benefited from large scale data, and whereas robotics has struggled to benefit from large scale data. So, I mean, I understand your concern. I know, I mean, there are ways to do structure and stuff like that. But for me, that's not a problem. For me, solving the 80% is the problem right now. Once I get to 80%, then I will think, so, okay, what's the last 10%? How I would do the thing as well. So, I mean, I know I chickened out of the answer, but yeah.
So I just wanted to ask, so this is a visual oriented approach, right? So, but when you think about how you interact with an object in the world, it's mostly tactile. I mean, once you decide what you need to do with it, you can feel it, right? So you can feel the microwave door, the resistance, it's how much progress has been made incorporating, like a tactile feedback. I mean, and do you think that would unlock more capability?
So, I mean, you're right. I mean, the only problem is in vision, I have a get around with the passive data. In tactile, I don't even have that get around. Because this, like in vision, there's all these Instagram images and videos of people doing how-tos and stuff like that. In tactile, that data set also does not exist. So tactile has to go through even harder motion of how to find its data to actually solve this big data problem as well, and so on. Now, I think the problem in the space of tactile has been generating a sensor itself, like the hardware of tactile, is a much harder problem than vision. In vision, you're not interacting with the objects, so wear and tear is almost nothing on a camera. In tactile, you have to interact with the objects, and your skin wear tears. Our skin can automatically repair itself, but that kind of technology does not even exist. So tactile has been going through very hard time because of the hardware issues, and the hardware issues is because of the wear and tear it goes through, because for tactile, you have to have this physical interaction. Without physical interaction, you would never have the sensing themselves. Interestingly, actually, we had something very recently in submission, which I think is very novel way of tackling this thing of tactile. So instead of using standard tactile sensors, we are using audio, like the audio sensors, the physical audio sensors, contact microphones as a tactile sensor. And now you can, so if this is a contact microphone here, when you do the information, you can hear the sounds like the high vibrations in the contact microphone. The beauty of that using contact microphone is, because it's an audio driven channel, you can actually use all the YouTube videos of audio to pre-train representations. And that's what we have shown, that YouTube videos of audio will transfer to the contact microphones of manipulation, like the sounds that you will hear in pressing a guitar or even moving a hand like this could actually pre-train representations. So we are thinking about, I mean, I agree with you that tactile is very, very critical. Until we do the tactile, it's going to be hard to get these last 20% and so on. Again, 80% I think we can do with vision, but 20% will be hard. And we are thinking of like doing these approaches of how to use YouTube data for tactile as well, with this intelligent microphone style tactile sensors as well, and so on. But I think this is a much more open area, even more open area than anything.
I guess I have two questions, one of detail and one a broader question. So I'll start with the question of detail. So in the affordance learning paper, there's a very surprising result in there, and I'm curious what you think of it, which is that synthesizing directly 3D hand poses works worse than first synthesizing pixels and then running a Frank mocap on top to extract the 3D pose. Can you give some intuition why that is happening? I mean, I found that personally very surprising. And
I mean, I think that is because we are able to use the stable diffusion models, which are actually like all the pre-training of the stable diffusion on the web, right? I mean,
I thought that doesn't represent the hands very well to begin with.
It doesn't represent hand very well, but it has some information, is what I believe. It cannot generate the exact pixels and so on. I mean, the question is, I mean, you can ask the same question in the other example, right? It was still able to generate spokes. So it knows that there are spokes in the chair. It's just that those spokes are not in a good configuration. So I think that a lot of information is hidden on those stable diffusion models. They're not good enough to generate good pixels out, I think, at this point of time. And that's why we imposed a structure. So I think still a lot of work is pulled by stable diffusion models. And it's just that the structure makes the image generation look nicer so that we can run Frank mocap on it and so on.
Okay. And I guess my broader question was going to be about the last set of results that you showed. there is also other sets of manipulation tasks which are more dexterous and such. Do you hope that we can actually transfer also for more dexterous tasks beyond, pick and place and in some sense kinematic tasks, right? Where, you have more contact dynamics involved and such. So I'm curious what you think about that.
Yeah, I mean, so actually I was just last night thinking whether I want to present this or not. So I do have the slides of that part also, but I'm not going to I'm just going to show you one example in the last. So, I mean, you can try to now go forward with the prediction of not just the mask, but actually much more dexterous predictions of how human hands are interacting with. So I think the future is here, that you're not just predicting mask, you're actually predicting the whole dexterous hand of manipulating objects. And you should be using these kind of fine level details to transfer to the robot hand and so on. We already know how to transfer static poses of hands to static poses of robot hands. We don't know how this motion thing. We are able to extract these fine-grained motions from videos now. This is a very recent ICCV paper. But I think we still need to learn how to transfer something like this to robots yet. I mean, we are not there yet completely.
Great talk. Very interesting. And building on some of the other questions here. So, you're training on humans doing tasks, and robots are not humans, right? They have different joints and all that. So do you think the robots that you're using will have some kind of identity problem where they think they're humans, but they have all these other joints than a human? And or you think that maybe this will drive robots becoming more like humans and you'll be able to better control them?
That I think is the way hardware progresses is actually something like that, right? I mean, you are constrained by software and the hardware progresses like that. Like in phones, right? All the phones in the world, might be manufactured by hundreds of manufacturers. They still have camera in the front, like back here, there's a camera in the front, you do all this. Why are all the manufacturers producing the same phone? You might be thinking. It's because your software has produced these constraints, and I think that will happen. Like if we don't have other ways of learning, and if we can only learn via humans, the form factor of robots will actually gravitate in hardware also towards more human-like and so on. But there'll still be a gap between what robot form factor would look like and a human form factor would look like and so on. But I don't think this is a huge gap to jump, because if you think of it the way children are, I mean, children bodies are very different from adult bodies who they are observing. Like even so they are able to do this kind of domain transfer, like from their big adult body to a child body is very different. They are able to solve these with domain transfer and so on. So I think the answer lies to me in both, that you have to do some kind of domain jump, but the world I think the hardware will actually gravitate towards more and more human-like by itself, just because of the nature of the problem. We will never have large-scale data for very special types of robots ever. And so it has to be better to be, these robots have to work in a human environment using human data. So why should not be they as close to humans as possible is the argument.
Hi, interesting talk. So I was thinking about the diffusion model problem that that people have shown, that you show the pictures of hands, shaking hands, and then there is this problem, right? That they cannot really differentiate the fingers and all that. And I was thinking, well, that looks like, you have two objects that integrate close to each other, and somehow there seems to be this mutual occlusion, and then it's hard to really predict where it is. But then I remember that you were also showing this robot at the beginning that you were capturing, which had two hand tasks. That was almost at the beginning when you were just explaining about how data should be generated in the past. And so, but all the tasks that you're showing now are just with one hand. So I wonder, how do you think that maybe there's ongoing work in your lab about two-hand tasks? Because now you had the mutual occlusion problem, right? That we even saw that the models are really good to, kind of show what a pose will be. And so do you have any thoughts about how two-hand tasks that are mutual occlusion and whatnot and more complex will perform with these methods of passive, I guess?
There's not much hardware out there actually that with two hands right now. There's one of two humanoids that are starting to appear now on the market, which can be used with two hands. So the hardware is the biggest constraint with two hands. You cannot just put two arms, like people do that, put two arms to pretend like two hands and do it. But there's not much hardware right now. I hate to do it, but I think it's again the truthful answer here is that we are nowhere close to solving one-hand problems. So, and that doesn't mean that we should not do two-hand problems itself. But again, right now the field is still focused on one hand because we cannot even do with like simple one hand problems still. I mean, they are very hard. The physics is very hard. They do not transfer. Most of the robotics result, I would say the top is trained on same object and tested on same object. That's the only level of this is for the first time people are talking about generalization in the last 1 or 2 years and so on to a completely new objects with one hand and so on. The good part is the hardware is progressing with software on the other end, and there's a lot of hardware revolution happening in China and other places right now. So if you go to any of the robotics conferences, there are at least 10, actually not even China, here also, I'm sure you are following Elon Musk and all these other companies like Figure AI, which are trying to generate humanoid and so on. So the hardware is actually progressing for the first time at a very fast pace. In, I would say, for the first 5 years of my robotics career, like 2016 to 21, there was almost no progress in hardware. But the last 2 years of hardware progress is much more than 15 years of hardware progress in the case of robotics. So the good part is that the hardware is progressing, and as soon as there is something of a hardware that like researchers like we who don't work in hardware can use with two hands, I think you will see things starting appearing with two-hand tasks and so on and so forth. Yeah, I think we are mostly bottlenecked by the hardware, I would say, at this point of time.
Abhinav, for a great talk.